Now we're going to start section 12.4. This is curve sketching techniques, and what we'll actually be doing here is doing the same stuff we did in 12.1 and 12.2, using the first and second derivative to get a whole lot of information, and then pretty much we just graph all that information. Now the graphing strategies, got some steps here. We're going to analyze the function, find the domain, find the y-intercept, and find any asymptotes. And this is all apparent if we can see that, quickly. And we should for sure be able to tell what the domain is and what the y-intercept. Remember, by definition, y-intercept is when x is equal to 0. We're going to, in step 2, use the first derivative. Step 3, we're going to use the second derivative. And all this information we're going to use to sketch the graph of the function. So, summarizing the pertinent information obtained by applying the graphing strategy and sketch the graph of f of x. I've got two examples. First example I've got here is f of x is equal to 10x times e to the negative 0.1x. This is an exponential function. My domain, I have no restrictions, so it's all real numbers. My y-intercept, if I put 0 in for x here and here, putting 0 in the exponent, I'm going to end up with 1 here. So I'm going to have 10 times 0 times 1, but I still end up with 0. Now I've got no apparent asymptotes yet. I want to explore a little bit more. When I have an exponential, I normally have an asymptote. So we'll check that out here in just a bit. So step 2, let's go get our first derivative. Since I've got 10x times e to another function, 2x, then I'm going to have to use my product rule. So I'm going to let u be my first factor, v be my second. Okay, now get your derivative. The u prime would be 10. V prime, if you remember, I've got 1 times, leave a space for the derivative of the exponent, times, and repeat your v. So I should have right in the middle a negative 0.1, and let's see if I do. There we are. So now I'm going to put it in the appropriate place. This is my product rule. So I've got v times u prime plus u times v prime. So there's my v times my u prime plus u times my v prime. Anytime I have an e, I'll always put the coefficient in front. So I'm going to have 10e to the negative 0.1x minus, and if you multiply this, 10 times negative 0.1, notice I've got my multiplication here, would give me a negative 1x e to the negative 0.1x. Now anytime you have e as either u or v, there's always that repeat feature, and I'm going to suggest strongly here that you factor out the e. So if I factor out the e, I have this. And I've got some stuff in my way. Okay. Alright. So, set this equal to 0, this piece right here. Now, usually if you have an e, this is the easiest route to go. Guys, e raised to a function of x or any exponential, just this piece right here, it will never equal 0. It is an exponential. Our normal exponentials will level off at the x-axis, but they'll never cross it. So this thing over here, my second factor, I can set equal to 0, and I have x equals 10. So now let me go put this piece right here into my calculator. So second ln to the negative 0.1x, and then put 10 minus x. I already know where it should cross. Now remember my window, right now it's a decimal window, so if I do zoom 6, I'll get some of this right here. but I had to extend this. So let me go back to my window, and let me make this 20 and see if we get where it crosses. Okay. And now if I go find my 0, which I can here, so 5's good, 15. So there's my 0, which I already knew. It's just quicker to solve these by hand because sometimes you really have to modify your window to see this. But notice before 10, my derivative is above. That's where my plus came from. After 10, it's below. So my original is going up, leveling, and coming down. So I'm going to have a max here at x equals 10. If you remember where to substitute that back in, go back to your original. So let's see what I've got here. So let me quit this. Let me store 10 in for my x. Let me go back to my original problem. I've got 10x, second ln negative 0.1x, and this will give me my maximum value. Okay? So let's see what I've got here. Whoopsie. Here. It is increasing. Anytime you have a plus for your derivative, it's increasing from negative infinity to 10, and it's decreasing from 10 to infinity. So that's your using your first derivative. So we've analyzed the function with that. So we've got to keep this point in mind. Now let's go get the third step here. Let me get this back on the other side where I wanted it. There we are. So here's my first derivative. I'm going to leave it in this form because it's going to be a whole lot easier for me to get my derivative, my second derivative. So this one's u, this is v. Get your u prime, your v prime. So my u prime should be 1 times negative 0.1 times e to the negative 0.1x. Remember to leave that space in the middle. My v prime should be negative 1. Since this is a product rule, I need my v times u prime plus my u times my v prime. So let's see if I put it in the appropriate place. There's my v, there's my u prime. If you need to make your dot bigger, do that, because I'm going to have to distribute here in just a second. And then u times v prime. I like this one, that one's easy. So that I can see the negative e to the negative 0.1x. So distribute that times 10 will give me that negative e to the negative 0.1x. Negative times negative is a positive 1x e to the negative 0.1x. These two can combine. They're like terms. Now if you'll notice, I've got e here and here. So let's factor it out. And remember, e raised to whatever can never equal 0. This piece can. So if I set that equal to 0, let's see what we get. Add 2 to both sides and then divide by 0.1, x equals 20. So you see that is still outside my window that I've got on my calculator right now. So it's just a whole lot quicker if you factor out the e's and then set what you have remaining equal to 0. So this is my second derivative, so let's go graph it. Clear out that one. Guess I could have kept some of it. So second ln negative 0.1x, close that for my exponent, negative 2 plus 0.1x. Let's go graph. Now remember, I know it crosses at 20, but if you'll notice, I cannot tell that by my picture. So I even had to, well, you can see the window I used here, but I had to really pull this, especially the y-axis apart. So I'm going to leave the y-axis right now as negative 10 to 10. make this 30. And when you start going up with bigger numbers here, you're going to have to make your scale a tad bigger. So I'll go by 2. Now remember, this is negative 10 to 10. And right now, if you'll notice, I can't see that it crosses. So I'm really wanting to focus on the x-axis, so I could care less how high these go. So if you'll go to your window, and this is what I call pulling apart the y-axis. I'm going to make it go from negative 1 to 1. And look what happens. Now I can tell that it does cross. And it crosses at 20. We can verify this by doing second trace for the calc menu, 0. And I'll put in 18. Whoop, go back. That's good. And say 22. And I don't guess. So this is why I think it's a whole lot easier if you do this. So let me see what my note is. When working with E, it's to your advantage to solve the equation. I had to modify the picture to your left 3 times in order to finally see that it crossed the x-axis at x equals 20, and this is the window, which is what I had up here. So with E's, I definitely think it's a whole lot easier to U-factor out and solve whatever you have left in parentheses, set it equal to 0. Now, using this picture, here's 20. To the left of it, my second derivative is below, so it means it's concave down. To the right of it, it's above, so it's concaved up. So my original curve is concave down from negative infinity to 20, concaved up from 20 to infinity. So I know I have a max. So if I had to do this by hand, I'd make sure I'd be able to get that point there. I'd go find where my inflection point. So let me quit this. Remember, this is my original. Let me store in 20. Do second enter, second enter. So my inflection point is at 27. So I'd have that point. I know that it crosses at 0, 0. I have that point. I have the point where it is changing concavity. And those really are about the only 3 points I actually need for this picture. So now this is the original. So if you go to y equals, let me clear out the second derivative. Since I've used the original twice, if you do second enter, it will paste it in. Now let me go to my window. Remember what my max was? It was around 37. So let's go ahead. I'm going to make this 50. And we'll go by 5. My y-min, let's do negative 10 to at least 40. We'll go by 5 there. And let's see if my graph should be the same. There it is. But if I was doing it by hand, I'd have that point where my y-intercept, I'd have the max, and I'd also have, let's see, remember we went by 5s, 5, 10, 15, 20, so right in here is where it changes concavity. So I'd have that point, and then I'd sketch and indicate this is my con. If you'll notice, it's dished up. Also notice, as this keeps going, if you make your window, let me get my x's just a tad bigger. I'll go to 100. Scale by 10. Look how this starts leveling off, which is the nature of an exponential, and it's leveling off at the x-axis. Okay? So that's that particular problem. Let me see. My last example is for a quotient. Now, if you remember my domain, I can use anything accept what leads to division by 0. So all real numbers except x can't be 0. Y-intercept, let x's be 0. I end up with 7 over negative 2, which is in decimal form 0, comma, negative 3.5. So a point I will be graphing. Horizontal asymptote, remember you compare your exponents. Since they're the same, it'd be 2 over 1. So remember it's y equals 2. That's from your first test, my vertical asymptote, when you set your denominator equal to 0. So I've got this information. So step 2, I'm looking at finding my derivative. So u is my numerator and v is my denominator. Let me move this down. Go find u prime, v prime. U prime should be 2, v prime should be 1. Since this is a quotient, I do my quotient rule. Remember, I always start with the denominator. So let me move it. V squared, then I have v times u prime minus u times, didn't move it enough, v prime. Remember, leave denominator alone. We're going to clean up the numerator. So distribute through the 2 and distribute through. Remember, this subtraction is going to change signs. So technically bring that 1 in front and distribute through a negative 1. The two x's are going to eliminate. Looks like I end up with a negative 11 over that quantity squared. If you graph this on Zoom 6, so let me clear that out. I've got a negative 11 divided by parentheses x minus 2 squared. Since we really messed up our window, if you'll do Zoom 6, it recenters everything. It is not defined here. If you set this equal to 0, it can never be 0. Okay? So I do have this partition number, which has to be on my sign diagram. And if you'll notice, to either side of 2, my derivative is below. This is where the negatives come from. So remember, your tangent lines are coming down, which means your original curve is decreasing. So it's decreasing from negative infinity to 2, and then from 2 to infinity. There are no max or mins. In order for me to have max min, remember, I have to go through a 0, and it has to be a positive or a negative, or if it's not defined here, but it is in the original, that's a critical value, but still my signs have to change. So I have no max or mins. Alright, now let's go get the second derivative. Hopefully you remember, it is to our advantage if we have a constant up front, or a constant in the numerator, excuse me. Move that denominator up so we can use the chain rule, and therefore, or thereby, I don't have to use the quotient rule. It's faster. So negative 2 times negative 11 will give me a 22. Rewrite, decrease power by 1, so I'd have a negative 3 there, times derivative of the inside, which would be 1. Okay. If you graph that, let's see if we come up with the same thing. I've got a 22 parentheses x minus 2 raised. I didn't hit the raise. There you are. Negative 3. Okay. Or you could put 22 over that quantity cubed. It'll still same problem. Okay. Still not defined here. If it's not defined in the original, it's not going to be defined anywhere through these derivatives. So I've got not defined at 2. My second derivative is below the x-axis to the left, above the x-axis to the right, so that's where my negative and my positive. And with the second derivative, if it's negative, it's concave down. If it's positive, it's concaved up. So original curve, there it is, concave down from negative infinity to 2, concaved up from 2 to infinity. There are no inflection points. So I don't have very much to graph on here. I can graph my asymptotes and get a couple of points that are nice. I do know the 0, negative 3.5. I could find this 0 here. So it's concave down, it is decreasing, and it's concaved up. So some problems give you a lot of information, and some problems don't give you that much. But the first and second derivative, it will indicate what your original curve is doing, and that gives us that pertinent information that we can use, so when we go sketch it, we'll have that. So you need to try some of these problems and let me know if you have any that you want me to do. Thank you.